All right, now it's time to talk about the Ethereum transactions in more detail before moving on to our next smart contract example, because once you understood how transactions internally work, then you already have covered a lot of bases for anything that you do on the Ethereum network with any kind of EVM. Okay, what did we do? We started a MetaMask transaction. So we used MetaMask to actually run a transaction, and the Ethereum transaction internally uses a couple of properties from an object that is being sent through either Web3 or Ethers.js, but usually they are the same properties. So if you have a look at the Web3 documentation, then you will see something like web3.eth.send transaction. This is something you will come inevitably across as a web developer. This kind of function is so important that I think it should be on the first page of the Web3 documentation. Now this one gets a transaction object, and this transaction object is, in this case, it's a JavaScript function that you call with a JavaScript object, and this JavaScript object has a from property, which is the address of the sending account. It has a to property, which is the destination address. And you already see here, this is optional. I will tell you in a second why. It has a value. So we send 0.5 ETH, which is 0.5 to the power of, well, times 10 to the power of 18. So it is not 0.5 that we send in there. This is denominated in Wei. That one is Wei. Important to understand that. It's always going with the lowest possible denomination, and the lowest one is Wei. Then we have, well, this one is the old transactions. It's gas and gas price. Now we have gas, we have the base fee, which gets burned. So this doesn't go to miners, and then we have a priority. This one goes to miners. And this one is actually the auction for how fast the transaction is getting baked in a block. Then we have a data field, which is also optional. And then we have a nonce, which is the integer, the amount of transactions that were already sent on the network, which is usually there. And if it's not there, then it's being filled in by the Ethereum, by the send transaction function itself in the background. This is just optional over here for Web3.js. Now, what happens over here if you don't send a to field? I will also show you this in the later lectures about the smart contracts. Then the data field must be populated, because then it is a contract deployment. Okay, data field populated, no to field, contract gets deployed. Okay, one more time, the most important things. From is an account, to is optional, value is an integer in Wei, and the rest we will talk about later as well. Then we had a look at the Ethereum transaction on Etherscan. So you saw the transaction hash, you saw the status, the block number. It's considerably lower over here because it's an old screenshot. From address, to address, the value, we sent 0.5 ETH, not 0.15, and so on. Transaction fee, and so on. So those things should be fairly understandable numbers for an Ethereum developer. So please make sure that you understand what is going on here. This is why I'm highlighting it so often, because when you are digging into failed transactions, and they will happen, especially with smart contracts, then there are a couple of numbers over here that tell you a few things about how the transaction failed and what might have happened. We have the from, we have the to, we have the value, and those are already the most important for just sending transfers. But how does the blockchain know that the transaction is not malicious? What happens there in the background? Or in other words, how does the blockchain know it's allowed to transfer like this amount of ETH, 0.ETH from my account 1 to my account 2. How does that work? Well, there is the answer. That is, it's creating a signature. And that happens with another function on Web3 that is web3.eth.sign transaction. And this uses an account in the background or a wallet. And this is where MetaMask comes in. So if you have a look at this raw transaction object over here, then we actually just said, hey, send from this address to this address this amount of way, basically, and the gas price and so on. That's the data we provided. But that is the actual data that is sent to the blockchain. So where is V, R, and S coming from? What is that? And that's the thing that we are going to talk about right now. So when you have a look at this transaction object, then you take it and you need a private key. And the private key is stored in MetaMask without really being visible for you, but it uses then a so-called ECDSA, elliptic curve digital signature algorithm, to create the public key. And from that public key, it creates the Ethereum account. So the Ethereum, that one, the private key, public key thing is actually very, very similar to how SSH connections work. So there's nothing super special there. The only addition here is that the Ethereum account is the KZAC hash of the last 20 bytes of the public key. So it's hashing the public key again, and it's taking the last 20 bytes or last 40 hex characters. So you have an Ethereum account now, you have a public key, you have a private key, and you have a transaction. So somehow you need to combine these two into something that creates a signed transaction. So you have these R, S, V values. That's the thing that you're after, or that's the thing that happens in the background. So once you have this, there is another function on the blockchain that is called EC recover. So elliptic curve recover. And what does it? It takes the transaction details that were provided. It takes the RSV values and it can recreate the Ethereum account. So that one is never shown to anyone. That one is known, and that's basically the from field. And the EC recover should be the same as the from field from the transaction object. And there you have it. That's how the whole magic works. So the really important part to understand is that you cannot give away your private keys. They have to be kept safe. So no matter who is asking for your private keys, don't give them out. The public key is something you seldom see. You maybe see the public keys when you're working with Go Ethereum. That's the eNode ID. But normally you don't see the public key. What you actually see on Ethereum is the Ethereum account that's publicly known. That's your account, so that everybody knows that. Now there's one more thing, and that's with, especially with MetaMask, what I said before, the seed phrase. The seed phrase is run through a special kind of algorithm and uses an index to create these private keys. So you can have a virtually unlimited number of private keys, and then a virtually limited number of public keys, and virtually unlimited number of Ethereum accounts from one seed phrase. So that one is the thing that works in MetaMask behind the scenes. Your 12th word mnemonic, 12 word seed that you hopefully wrote down and kept somewhere safe. And then from this one, the private keys are generated. And when you say in MetaMask, hey, give me a new account, then it will use the seed phrase, increment the account index, create a new private key, create a public key in the background, hash it, take the last 20 bytes, and then have the Ethereum account. This is what happens in the background in the wallet functionality of MetaMask. So keep the private keys safe, but please keep the seed phrase even safer. So never give it out. There is no MetaMask support that will ever ask for your seed phrase. So if there's maybe one takeaway from this course, keep the seed phrase safe. It's meant for recovery. It's meant for your eyes only and nobody else.